finite injury. The idea with finite injury is one that I think we've already seen or mentioned a bunch of times. So, in general, a finite injury argument will be the form you're trying to construct something. You have a collection of requirements, Ri. I is a natural number. So here it seems like all the Ri, like it's a uniform set of requirements. Usually your your requirements come in a variety of flavors, but then you take all these flavors and you introduce one ordering on them of order type natural numbers. Why order type natural numbers? Because order type natural numbers has that every one of these requirements has only finitely many that are less than it, and so the further to the left is higher priority. I.e., if you order everything in order type natural numbers, then for every requirement there are only finitely many requirements that you consider more important, that have higher priority. So what does that mean? Well, here's your requirement I, Ri, right? 0, 1, 2, and your requirement Ri gets to do whatever it pleases, as long as it doesn't injure the higher priority requirements. Right? Injuring a higher priority requirements is something that is part of. Right? When we write down a requirement, then we start analyzing the requirement. In this analysis of the requirement, we come up with a basic module. In the basic module strategy, there is indicated that under these sort of circumstances we take the following action, and under these sort of circumstances we require the following to happen. And require the following to happen is indicating towards the lower priority requirements that they don't get to do certain things. The usual type of action of this second form is to introduce some restraint on a set. Requirement R2 will do some computations and then find out that well, this particular computation I really like, and I want it to stay the way it is. Well, this particular computation uses an oracle A, and it uses part of this oracle, right? With the use function you can see which part of this oracle is of importance. And then part of the actions of requirement 2 can be impose the restraint R, this much of A now no longer gets to change. Now R3 and the lower priority requirements have to obey this restraint. R0 and R1, they don't have to obey this restraint because they are higher priority, they are more important requirements, they get to ignore what R2 wants. So now, what are the things you want to see? Right? If the restraint by requirement R2 is little r2, let's say it's a restraint on some set A, then commonly what you want to see is this restraint. It'll change sometimes, right? It's something about protecting a certain computation. And then if R1 injures this computation, then the computation goes away, and maybe at some later time R2 finds a new computation it likes, and therefore introduces a different restraint at that time. What we want to see is that these values of the restraints stabilize to some finite fixed value, because that says for all the requirements of lower priority, okay, there is this initial segment of these sets which you don't get to touch, but there is infinitely much of these sets you get to work with. And then the basic module will be such that that is sufficient. Okay, an infinite injury, it is finite injury because every requirement gets injured only finitely much. So what we need to see is that this Ri gets injured only finitely much by the requirements that are less than it. One of the easy situations is going to be like in the first theorem we're going to do it is showing the existence of a low set. Existence of a low set meant, well, if you find something in a certain CE set, then you stick it in a set A. And once you do that, the intersection of the CE set and the set A is forever non-empty. And so each of these requirements that are of higher priority get to act exactly once. No, get to act at most once. And once they act, they are permanently satisfied. And so Ri only gets injured by the ones that are less than it. And we'll therefore be able to conclude that Ri gets injured at most I many times. And then the inductive argument progresses from there and it all works out. Okay, that's an awful lot of abstract hand wave, but it kind of lays down the basic terminology of what finite injury is. And then we'll get to see how it works out in practice by proving an actual theorem. Are there already questions about the abstract impressionistic hand wave?
When you say that it's injured finitely many times, does that mean like the set for which it's satisfied is injured in finitely many places? Or does that question not even make sense?
Injured, I think in the abstract, injured should be thought of as something just determined by the basic module that says when something is injured. So if there are restraints like this, something gets injured if something changes below a restraint. In other contexts, what injury means is less clear and fuzzier. I forgot your question. Did I answer it already?
I think that you'll necessarily answer it by doing a proof with this.
Well, but this is sort of the general impressionistic picture. In any proof, specific things will happen that are not necessarily part of the generic method, right? But I suspect the question will disappear anyway once you see a real proof. You see what goes on, and you see how it actually works out in practice. Okay, theorem. There exists an A which is both simple and low. Right? And now we know that both simple and low we have dealt with before. What was the simple strategy? Well, the simple strategy was make sure the complement stays infinite and look at these CE sets, and whenever something appears in the appropriate CE set, you put it in A. And this has a tendency of putting too much in A, so you have some restraint from putting too much in A. For the low, well, the only situation I think where we constructed something low was in the low basis theorem, where we were looking at trees, and then you could thin out the tree to make a certain step in the jump determined. This tree idea isn't quite of the right type to put in restraint version, so we're going to come up with at least a very different sort of requirement for the lowness. Okay, first of all, for simplicity, if WE is infinite, then WE intersect A is not empty. Right? That's not quite entirely. It's not the case that if you satisfy OPE you are simple, because the set of all natural numbers satisfies OPE. But that's why we have these other requirements. CE, which says that AE is equal to the limit as S goes to infinity if A as E exists. And so this says that we're doing this construction, it goes along in stages. At every stage you have an increasing enumeration of the complement, right? These are the movable markers. And requirement CE says the eth movable marker does not move infinitely much. And our analysis of the whole movable marker construction was exactly that the set we are constructing is co-infinite if all markers come to a rest, and otherwise it's co-finite. So this requirement CE is exactly of the right type to ensure co-infinity of the set A using the movable marker idea. So these requirements together, well, all infinitely many of them, do make A a simple set, right? The complement is infinite and does not contain any infinite CE set. So that takes care of half of what we want. Simple. So then we need low, and the lowness requirements are kind of interesting. What does low mean? Well, low means that you have to be able to decide when this convergence happens. Well, you don't have to be able to decide it, because right, not a single jump is computable. You have to be able to decide this using zero jump. Zero jump should suffice to answer the question of whether element E is in the jump of A. That's what we want for lowness. Now, of course, this is not something you're likely to have access to at any point in the construction. But what you do have access to are the sort of the approximations to it. Right? We are constructing this set A, and the approximation to the set A at time S is called AS, and then we compute it for S steps, and checking whether or not this converges is a computable question. Right? We have this computable approximations for the sets AS, and we can always compute this. Now the lowness requirements say that if there exist infinitely many stages S where this converges, then we want the final thing to converge. So in general, of course, this doesn't have to be true, because it could be, depending on the exact meaning of the set of S, of the parameter S, but modulo that, if you allow me, it could be the case that whenever S is even, this converges, and whenever S is odd, it diverges. Right? You could have this computations just accidentally work out like this, that at the even stages, just enough of the oracle gets enumerated that you converge, and then at the odd stages you stick something in which makes it diverge. But then at the next even stage you stick something in which makes it converge again. And then you converge and diverge alternatingly all the time. And then this is not going to happen. Right? Because when this happens, if the final result here is true, if this computation converges, then there exists a finite computation that looks at a finite part of A and this finite part of A at some point needs to stabilize. So this picture I just described of converging at the even stages and diverging at the odd stages is exactly the picture you want to avoid. You want to make sure either from some point on you diverge, that's perfectly fine, and you'll diverge in the end as well, or from some point on you converge and you keep converging with the same computation and nothing changes about it. Okay, so if we satisfy requirements NE, why is the set low? Right? Well, the set is low because using zero jump, you can ask at time 0, is there going to be a time in the future when I converge? If the answer is yes, then you go to that time, and then at this time you use zero jump again, and you ask, is there a time in the future when I'll start diverging? Is there a time in the future when I converge? So that you can alternatingly go like this and search for the time when convergence or divergence has stabilized. And then you have the final answer to this question. So zero jump gives you this way of if NE is true, right? If this requirement is true, then every E has only finitely many alternations between convergence and divergence. And then you just search through them step by step using zero jump until you have reached the final state, and the final state is exactly what the real final state is. So I think that argues that if I can satisfy all these requirements, I win. Then I have an A which is simple and low. AS satisfies all requirements, then A is simple and low. Everybody happy with that? Well, I said AS here because NE of course depends on the approximation. Oh, so the C. Good. So this is step 1 in the process. We have come up with the requirements and figured out that we have at least a sufficient set of requirements. Okay, now we order them in order type of the natural numbers. And just pick something, right? The P naught, C naught, N1, N naught, P1, C1, N1, and right, you just order them in some way. And I really, honestly, don't care how you order them, but this dot, therefore irrational, right? You should probably not repeat your requirements, that would be a little funny. Just order them in any way in type of natural numbers, and that'll do. If you do it in this sort of regular way, your analysis will likely be better than if you choose something which is terribly messy, right? But I'm not going to go into that much detail of the analysis anyway, so it won't matter at all. So now we have our requirements, we have them ordered. What does it mean we have them ordered? Well, now that we have them ordered, we know how these requirements get to act. Requirement N1 gets to do whatever it pleases as long as it doesn't displease any of these requirements before. Right? And we haven't defined the basic modules yet, so we don't know what these words really mean. Displeasing the ones before, right? Means injuring the ones before, but in the basic modules it will become clear what that means. Okay. So, basic modules, what do we want? the PE are you've seen it before, right? What do you do with PE? Well, you wait for an X in WE while WE intersect A are empty. This is not the most beautiful formulation you can come up with, but right, you wait for something to appear in WE as long as it seems the requirement is not already satisfied. As soon as the requirement is already satisfied, it's satisfied and you don't do anything anymore. But if you find an X in WE while WE intersect A is empty, then you want to enumerate X into A. Right? It's the same basic module for this requirement we've seen many times before. CE. CE, well, what does CE do? CE wants AE to stabilize. How do you stabilize AE? Well, it just says restrain A up to AES 1. It doesn't do any positive contributions to A. All it does is it say, I'm happy with whatever all the other requirements do, as long as they do not take marker AE or smaller and move it from A complement into A. Right? So all it does is insert this restraint. So what does this mean in the construction? Well, in the construction it means that here is requirement CE. These requirements don't care. Right? They are higher priority requirements. They could not care less what CE desires. These requirements up here can only work above AE. They get to do whatever they please with A as long as they're above AE. This is exactly the intended effect of CE doing this. And NE is very similar. What is the basic module for NE? Well, what do you want? Right? There's nothing you can do to make this converge. Maybe sometimes accidentally there's a Turing machine given to you where you understand how you could make it converge, but in general you have no hope to do positive work towards making it converge. But what you can do is stand back and wait for phi ES AS E to converge. If it doesn't converge, you don't have to do anything because it doesn't converge, and if it keeps not converging, then everything is good. If it does at some point converge, then remember how we looked at this idea. If it does at some point converge, then we wanted to preserve that particular computation of the convergence. That was the big idea. Well, we know exactly how to go about preserving that sort of computation. If this happens, then restrain A up to restrain the part of A that is used in this computation. And in exactly like this analysis here for CE, we have the same thing for the requirement NE. The ones to the left of it shouldn't care, and the ones to the right of it need to work with A only above this use. And if that is how they behave, then this is preserved. Okay. So now we have basic modules in isolation. So we need to adjust them a little bit to see that they can work together. Or how do you make them work together in general? Well, these two requirements, all they do is restrain something. Clearly, if your only action is to restrain something, you don't injure anything. Injury in this particular proof, injury means enumerating something into A below the restraint. Because as soon as you enumerate below the restraint, well, it is not guaranteed that this computation will no longer converge, because maybe you enumerate something in there which is not one of the oracle questions asked. But that's not the kind of subtlety we want to deal with. We just want to say, if you enumerate below the restraint, you injure the computation. If you only enumerate above the restraint, you don't. CE is different because clearly any enumeration injures CE if you're below the requirement. The only thing it's trying to do is make the markers not move. If you enumerate, the markers move. Right? Here, if you enumerate, the computation might not be injured, but we're going to pretend that it is anyway. So CE and NE, these require no change or addition to work well with the other ones. NE, you just have to say, wait for x, x above all restraints of lower requirements or higher requirements.
Higher priority.
Higher priority, lower index. Let's just say higher priority. But the lower index requirements are the higher priority requirements. Plus P is bigger than C is bigger than N. Everybody happy with all of these so far? Good. So now if you look at this, you should already become pretty satisfied about things, because it looks pretty good. We have these requirements, we have a good idea of how they interact. So now we just need to finally prove that they work. They look like they work, right? Not convinced.
I don't see any problem with
I don't see a problem either. So now, of course, the question is, how do you prove that it works? What do you need to prove that it works? Well, right, all requirements are satisfied. Now, in earlier proofs where we've done things like this, we would say something, well, we prove that all PE requirements are satisfied, and then we go and we prove that all CE requirements are satisfied. But in this case, it doesn't really work that well, because the way PE plus 1 gets satisfied rather depends on what happens with CE. Right? If CE is not satisfied, then small changes keep happening to A, and the restraint keeps going up, and these restraints, if these restraints keep going up by the earlier stuff, then you can satisfy it. So this means we want one lemma that says for all E, PE, NE, and CE are satisfied. They all interrelate to each other. And then you see this, and my undergraduate classes can usually tell me, so how do you prove this? Well, for all E natural numbers, so induction, right? Induction on E. Now I'm mostly going to end wave because the details are really not that interesting. Oh, I'm being a little fuzzy. All of these are satisfied. Should have introduced some notation. Let's call this restraint CES, and this restraint here imposed NES. All of these are satisfied, and the limit over S of CES exists, and the limit over S of NES exists. We are, in some sense, this is the point of doing the induction of all of them together, because then you can assume these requirements are these restraints exist. Okay, base case. P0 is the highest priority requirement. It has to find an X above all restraints of the higher priority requirements. There are no higher priority requirements, so it just has to find any X whatsoever in WE and enumerate it into A. Well, unless something else already accidentally did it. But either way, P0 is clearly satisfied like that. C0 says restrain A0, right? Make sure that A0 doesn't move. Well, it doesn't move from some point on. So what is now the typical type of argument you do? Well, you say, I have finitely many requirements of higher priority. By induction, I presume that each of these finitely many requirements of higher priority get injured only finitely many times, stabilize their restraint functions, and do their thing. Right? If I have finitely many requirements that need finitely much time to do their actions and stabilize their restraints, then I can say, well, look at the time t where all of these earlier requirements have acted and stabilized and have done their thing. This time t, by induction, exists. So, for the CE requirements, just look for the time t, or for the C0 requirements, look for the time t where WE intersect A is non-empty, if it ever happens, or time is 0 if it never happens. Right? W0 in fact will very likely be an empty set in any reasonable enumeration of Turing machines. So wait until that has stabilized. Now look at CE. Well, now CE imposes its restraint. All the other actions that are going to be done are by lower priority actions, therefore preserve the restraint. And therefore now at this time we just found this restraint CE has achieved its final and permanent value. Therefore, it will both, CE both will be satisfied and the limit of this restraint exists.
Are you presenting today?
Okay, and now we do the same argument again. Because it turns out, even though the any requirements look a lot more complicated, their action is very similar, right? Wait until something nice happens, set a restraint. So how do we show these any requirements are satisfied? Well, look at all requirements of higher priority. For all of these, we have assumed by induction that their restraint functions eventually stabilize. So look for a time where all of these restraint functions have stabilized. All of the PE, they act, if they ever act, they act as most once. So now look for a time past the time where the restraints have stabilized, where all of the ones that will act have acted. And now you have found a time where nothing of higher priority than the particular NE currently under consideration will do anything at all. The restraint functions have stabilized and the enumerations that will be done have been done. So then at this time you set a restraint, and this restraint will be respected by all future action. It being respected by all future action means that this restraint will not get injured, therefore will not change, therefore the limit has stabilized. Also, I'm lying a little bit. Okay, 2 steps back. So we can find a time where all the restraint functions have stabilized and all the action that will be done by the higher priority things have been done. Right? This is the time t. All the earlier stuff is in good working order. Now we start looking at what does NE do? Well, either NE is automatically satisfied because this computation never converges. That was exactly the case I was forgetting to mention. Either it's automatically satisfied because it will never converge, in which case we're happy and everything's good. Or at some point in time this convergence will happen. And then as soon as this convergence happens, we impose a restraint that will never get injured. Therefore this restraint has its final value, the limit exists, and because it will never get injured, this computation is forever preserved and the requirement is satisfied. That's pretty close to an actual argument for these things. But notice this sort of do induction on everything together, so that you can presume things about all lower order, all lower priority, all higher priority, all the requirements that are to the left in the ordinary picture, right? All the higher priority arguments. Because we do this by induction, you can presume I'm looking at requirement E. All the higher priority arguments have done their thing. And then we start acting. Okay, good. Notice that the argument is this time t that I talk about in the argument. It's of course not a time t you can find effectively. There's lots of halting problems in between. Will requirement PE ever find an X that will need to be enumerated? But the verification, this part, doesn't have to be effective. The construction has to be effective. The verification is just checking that your constructive work works. Now, often very interesting is this set, i.e. the set of times where RE gets injured. In some not entirely unreasonable sense, the size of this set IE measures something about the complexity of the construction. What happens in our particular case here? Well, the size of IE is always less than or equal to E. Right? Because requirement PE, CE or NE, when do these requirements get injured? They only get injured by requirements of higher priority. And when does something actually get injured? Something actually gets injured when PE finds an X that works. And once it has done something, it's not going to act again, right? That's why we have this protection on here. Without this protection, many PE will infinitely often enumerate something. But because we have this protection, only think about enumerating x if the requirement is not yet satisfied. This shows that every requirement PE except only once, and because this is the thing that needs to be taken care of, it can't get injured, right? Once you have taken an x from WE and enumerated it into A, no later additional enumerations into A will take this x out. Right? Nothing here says take x out of A. So that shows that the only injury that happens in this construction is by the e-many PE of higher priority, and each of those acts only once and then is forever satisfied. So the injury set for any requirement is bounded by E. This will certainly be different in later construction. I think even the next construction already has that these injury sets are of exponential size. So how does this happen? Well, this happens when your basic modules for PE are such that when PE acts, it could ruin the work PE plus 1 has done, and then PE plus 1 has to act again. And then you have, for instance, PE and PE, maybe PE plus 1 acts first, then PE acts and ruins its work, then PE plus 1 has to act again, and then you can get bigger functions in here. Questions? I think this is a pretty nice example of finite injury argument. Also the strategy here described. Come up with some requirements, come up with some basic modules, change the basic modules around just a little bit to make them work well together, and then do this sort of joint induction on all of the requirements to do it. And clearly you should do this a lot more carefully than I just did, but I think I certainly touched on all the ideas you need to see how these requirements interact and work together.